So whenever we were using the retail mart transactional data and the participants tagged as to whether they were pregnant or not, and we were sort of using that data to train a regression model, that is, we were using those data to solve for those model coefficients, we had to use the evolutionary solver. And there was a specific reason for that. Now, whenever you're doing regression in the real world, you may use the normal equation, as we discussed in a previous video, or you may use another type of solving algorithm to figure out what those model coefficients are. Now, there's a clever way to frame the way in which you compute those model coefficients such that you can solve for them pretty easily. And I want to start talking about something called a cost function. I've also heard it called a loss function. We're going to call it a cost function. And just imagine this x-axis down here representing all possible solutions for all of those model coefficients. Okay? And imagine this y-axis is our error. And when we did that regression, this y-axis would have been represented by the sum of squared errors, and then this x-axis here would have been represented by all possible values, the combination of all possible values for the regression coefficients. Now you can see as we change those values for the regression coefficients, we get more or less error. And there's an algorithm called gradient descent. And we haven't talked about gradient descent, but I just want you to know that vocabulary word. So gradient descent is an algorithm that picks an initial value for the model coefficients, and then it actually step by step finds wherever the lowest point on this function curve is by iteratively just going down the curve, sort of descending down the curve. That's why it's called gradient descent, until it gets to this bottom point. So it goes down at an interval that you can specify, and it'll stop whenever it doesn't get any better. So it'll find this. Now this cost function right here is a convex cost function, and the reason is because it only has one sort of little valley here, and we call that valley an optimum. It can also be called a minimum, and the reason is because that's where there's not very much error. Now this is a convex cost function. Here's an example of a non-convex cost function. You could see if you tried to use the gradient descent algorithm, where you're going to be specifying an initial solution and it goes down the gradient, it could get stuck in one of these. So you can see down here at the bottom there's an optimum, and we're going to call that the global optimum. And these other ones are called local optima because they're good solutions compared to the places they're neighbors, but in real life there is a best solution down here, and using a gradient descent algorithm you're not going to be able to get to that. Now we set up our problem in a non-linear way in Excel when we used the retail mart data, and so we had to use the evolutionary solver. And the evolutionary solver is different from gradient descent in that it picks different solutions all over this cost function, and then sort of there's some randomness to it, and it just tries to search all over the place for the best optima, and it tries to find the global optimum, and it may not. The evolutionary solver may not find that global optimum. So in a non-convex situation, you're going to be using some genetic algorithm or evolutionary solver or something like that. But oftentimes the problem can be framed such that you get this convex cost function where you can find that solution. Now, if you're using the normal equation to solve for your regression coefficients or your model coefficients, you don't really even need to think so much about the cost function, because you're actually solving for those optimal values analytically rather than using an algorithm to search around for to sort of tinker around with the values and pick out the best value. So I wanted to mention that. It's an important term, cost function. You can apply this metaphor to not only just machine learning, but lots of different aspects of decision making.